Hello friends, in this lecture we are going to learn about solving time-independent Schrödinger equation using some numerical technique. First, let us understand why do we need this. So far, we have solved analytically. For example, we have solved for particle in a box, we have solved for harmonic potential, we have solved for free particle, etc. However, if I have to solve for a double well potential like this, we cannot just solve using the analytical method. We have to use some numerical technique for that. The method that we are going to learn was given by numerical. Although this is a method which can generally be used to solve any second order differential equation, our discussion will remain focused on solving the time independent Schrödinger equation. So let me again state the problem. For example, let's assume that this red line is the potential given to us, and this looks like some double well potential. And as I just mentioned, we cannot solve the time independent Schrödinger equation analytically for such a potential. So the potential is given to us, and then we have to find the solution, the psi of x for this given potential numerically. So let us see that how do we approach the problem. So the time independent Schrödinger equation is minus h cross square by 2m d2 psi dx square plus v of x psi of x is equals to e times psi of x. Now, as we did before, we just rewrite this d2 psi dx square is equals to minus 2m by h cross square e minus v of x psi of x, and this part we just write it as p of x, right, such that we can just write minus p of x psi of x. Now keep in mind that v of x is given to us, so that means p of x is also given to us. Thus, we have to solve psi of x from this equation, and v of x is given. That means if I know e, then p of x is also given to me. The first step that we take is we divide the entire region in finite number of grids. So you see, this is the entire region. You see this straight line. This defines the region where we have to solve psi of x, and then the entire region is divided in small regions of width delta of x. And then since the function vx is given to us, we know the value of the potential at every grid point. And now, as I said that if we know e, then we also know this function t at every grid point. Now, also we can represent the differential equation in discretized form at every grid point. So you see that this is like d2 psi dx square is equals to minus px psi of x. So how do we write the discretized equation? So for example, I can take some grid point n, say I take this grid point, and at this grid point, we can write this equation as psi 2 dash 10, the second derivative of psi at the point n. and this is equal to minus Pn. So this is the value of the function at point n times psi of n. This is the function at point n which we have to solve. For example, if I take grid point number 2, the discretized equation looks like this. Psi 2 dash is equals to minus P2 psi 2. And then similarly at grid point 3, this equation is like this. At grid point 4, the equation is psi 4 2 dash is equals to minus P4 psi 4, etc. Let us assume that we know the value of function at this point, the function as well as its derivatives. Now, the question is, based on this information, can we know about the function at adjacent points? For example, at point n plus 1 or at point n minus 1. Taylor series expansion will help us to achieve this. Let's write the first derivative, psi n plus 1 minus psi of n divided by delta of x. This is the first derivative at this point. Now let's assume that I know everything about the function at this point n. So that means I can write psi n plus 1 is equals to psi n plus psi n dashed delta x, and then I can even add additional terms, higher order terms, for example psi n 2 dashed delta x whole square and so on. So this is known as Taylor series expansion, and as you see that if you know about psi of n dashed, psi of n 2 dashed, etc., then you can know about the value of the function at the point psi n plus 1. So this is known as the forward expansion. We can do it for this point also, and then that will be known as the backward expansion. Thus, what we do is that we take the function psi and we write the backward Taylor series expansion and forward Taylor series expansion for this. After we do backward and forward Taylor series expansion up to the third order, we just add them up, right? So if we add this term and this term, this is the equation that we get. Remember that in actual numeral method, up to fifth order term are kept. However, we will keep only up to third order term, and that will be sufficient to understand the concept. Now, let us see that how do we solve psi from this. So we got this equation by adding the forward and backward Taylor series. Now, if we put n equal to 1 in this equation, what we get is psi 2 is equals to 2 psi 1 minus psi 0 plus psi 1 2 dashed delta x square. So that means if someone gives me the value of psi 0, psi 1 and psi 1 2 dashed, I can find the value of psi 2. So that means if I know these two values, psi 0 and psi 1, I can get the value of psi 2. Similarly, you put n equal to 2, and this is the equation that you get. And then again, you see that to get psi 3, what I need psi 2, psi 1, and psi 2 2 dashed. So that means if I know about the function at psi 1 and psi 2, I can get the value of psi 3, and so on. So we can keep doing this, and then you will see that you will generate the entire blue curve by doing this. So essentially, what we are telling is that if we know psi and psi 2 dashed at a point xn, then the method will allow us to get the function at the next point xn plus 1. So far, what we have done is true for any function psi. Then the question is, where is my time independent Schrodinger equation. Remember that we are looking to solve discretized time independent Schrodinger equation given by this. And now via forward and backward Taylor series expansion, what we obtained is this equation. Now note this second derivative term in this equation and note the discretized time independent Schrodinger equation. So that means in place of psi and 2 dashed, we can replace this. So let us do that. So psi of n plus 1 is equals to 2 psi n minus psi of n minus 1. And in place of this, I replace this equation. So this is like minus Pn psi n delta x whole square. And then we can just rearrange this equation and write psi of n plus 1 is equals to 2 minus Pn delta x whole square psi n minus psi n minus 1. So we are going to use this equation repeatedly to solve for the wave function. Let us put n equal to 1 and that gives us psi 2 is equals to 2 minus P1 delta x square times psi 1 minus psi 0. So that means if I know the value of psi 0 and psi 1, using these two values, I can get the value of psi 2. And similarly, put n equal to 2, and then you see that value of psi 3 can be obtained if I know the value of psi 2 and psi 1. And we keep doing this, and then that will give us the entire curve. Now, you know that I must know the value of Pn at every grid point. Now, this value is known provided we know the value of E. Now, what is the value of E? Is it given to us? The answer is no. We have to solve psi as well as the corresponding value of E simultaneously. So, we already know how to solve for psi. Let us see that how do we simultaneously solve for the corresponding value of E. To solve for the energy eigenvalue, we use number of nodes of the wave function as an input parameter. Why do we do this? Because we know that the number of nodes of the wave function, they are related to the energy of the particle. For example, number of nodes is equals to 0 for the ground state, number of nodes is equals to 1 for the first excited state, number of nodes equal to 2 for the second excited state, etc. Now, we take some initial guess that the energy lies within this range E min and E max. In this figure, you can see that the initial guess, the E min and E max values are here. And then the assumption is that the actual E must lie within this range. Then we start a loop with the guess value of energy, and that value is taken to be the average of E min and E max. So for example, if E min is here and E max is here, then the guess value of energy is here. So that is given by this red line. Now, with this value of energy, what we do is that we solve psi of x by using numerals method. And once we calculate the psi of x, then we calculate the number of nodes of that particular psi of x. And that number of nodes in this figure is written in red. And now what we know, we already have set the value of nodes that I want in the actual wave function, and that number is set by, or that number is shown by this blue color. So number of nodes NON in red, that is something that I get from my guess solution. and NON in blue, that is the actual number of nodes that I am looking to find. And then you see that in the general, they will not be equal. For example, in this case, you see, let's assume that the actual energy value, the actual value of energy is given by these blue dots, right? So you see the guess energy is less than the actual energy. So that means the number of nodes that I get from this guess wave function will be less than the actual number of nodes that should be there in the wave function. And then in this case, what we have to do, so that means I need to increase the energy. So how do I do that? I shift the lower limit to here. Okay. And in the next cycle, this is my energy range, right? So this is my Emin and this is the Emax. And then what is the guess value of energy? And then the guess value of energy is now lying here. And again, I solve the psi x using the Numerov's method. And again, I calculate the number of nodes. And then again, I check whether that is matching with the actual number of nodes or not. And in this case also, it will not match, but because still the guess value of energy is less than the actual value of energy. And then what I have to do? Again, I have to increase the energy. That means I just shift the lower limit to the higher value. And then again, I calculate the average. And now you see that the guess value of energy now is more than the actual value. So that means with this value of guess value of energy, if I solve, then the number of nodes that I get is now actually higher than the actual number of nodes. So in that case, what we have to do, now we have to shift the upper limit to a lower value and so on. So this will keep going as long as my number of nodes, right, the NON is equal to NON, right? So when we achieve this, at that point, we are going to stop the loop. And also you see that as we keep doing this, the lower limit and upper limit, they will keep moving towards each other. And when do we say that the calculation has converged? When the difference between this upper limit and lower limit is a very small number, for example, 10 power minus 10. Right? At that point, I say that, okay, the wave function has converged because the lower limit and upper limit, they are very close to each other. And also the number of nodes, they are also matching with the desired number of nodes that I set initially. In that case, I say that the loop has converged and then the solution has been achieved. We are going to solve the time-independent Schrodinger equation numerically for two symmetric potentials. The first one is harmonic potential, for which we know the analytical solutions. We can match the numerical and analytical results to verify whether code is written correctly or not. In case of a symmetric potential, V of x is equals to V of minus x. And as a result, the eigenfunctions are either symmetric, that is psi of minus x is equals to psi of x, or they are antisymmetric, that is psi of minus x is equals to minus psi of x. Thus, it is sufficient to solve for only one half, say x greater than or equal to 0, because the other half is related by symmetry. For example, if we solve for x greater than 0, that is in the shaded region, we also get the eigenfunction in the unshaded region, that is x less than or equal to 0, because of the symmetry of the potential. The values of the potential V0, V1, V2, etc. are known to us. If we start with some reasonable initial guess of psi, then we can get the eigenfunction at psi1 psi2, psi3, etc. using the numerical method, and that will give us the entire eigenfunction. We are going to solve for another symmetric potential, the double well potential, which has a general form of Vx is equals to minus ax square plus bx to the power 4. The plot shown here is for a is equals to 6 and b equal to 1. Unlike harmonic potential, which has only one energy minimum at x equal to 0, we have two different energy minima at x is equals to plus minus square root of a by 2b. So one minima is here, the another one is here. It is straightforward to find the minimum value of the potential energy given by V min is equals to minus a square by 4b. This is also a symmetric potential, that is V of x is equals to V of minus x. As a result, eigenfunctions are either symmetric, that is psi of minus x is equals to psi of x, or they are antisymmetric, that is psi of minus x is equals to minus psi of x. Thus, it is sufficient to solve for only one half, say for x greater than or equal to 0. Note that unlike harmonic potential, we do not have any analytical solution. Thus, numerical solution is the only option in this case. Similar to the harmonic potential, there are two classical points in case of double well potential for energy greater than 0. For example, I have shown here the fourth excited state energy, which is greater than 0. And you see that there are two classical turning points in this case. However, for E less than 0, there are four classical turning points. In this plot, this is the ground state energy, and you see that in this case, we have four classical turning points. Two classical turning points for x greater than 0 and two classical turning points for x less than 0. Finally, let me quickly summarize what we have done so far in this lecture. Numerical solution of eigenvalue and eigenfunction of time-independent Schrodinger equation has two parts. In part 1, we guess some value for E and solve for psi using numerical method. Thus, if we know the value of psi at point n and point n minus 1, then we can find the value of psi at point n plus 1 because we know the function p of n. The function p of n is given by E minus V of n, and we know the potential at every point n. While calculating P of n, we start with some guess value of energy. In part 2, we have to get the correct value of energy iteratively. And we do this by matching the number of nodes psi to get the correct value of E. In the next lecture, we shall learn to write a code for harmonic potential and double well potential. The analytical results of harmonic potential are known such that we can verify our code by matching the analytical and numerical results. Once we are confident that our code is working fine, then we will apply the code for double well potential to get the energy eigenvalues and eigenfunctions.